Well, welcome back to Distributed and Multi-GPU Deep Learning. We'll be continuing our discussion on distributed training using TensorFlow. So distributed training. So previously we discussed how we can use the mirrored strategy in the case where we have a single node or single worker with multiple GPUs on the same machine. So in that case, actually, we only have one single CPU that's coordinating the training. But in the case where we have actually more worker nodes, there are multiple GPUs. So the way to actually do this is to actually use the other mirrored strategy, which is a multi-worker mirrored strategy. So this is different from the mirror strategy in the sense that there are multiple workers in this case. So the configuration is not just GPU 1, GPU 2, or how many GPUs they need. You also need to specify which machine or which worker node is that particular GPU on. So the way that we actually define this is to use the TF config environment variable. And you notice that actually we are putting a JSON definition where we specify the cluster of machines and the host and port numbers of each of the machines. And also we are specifying, yes, the cluster, right? The worker, where are the hosts and ports for each of them. So there are actually three worker machines in this case, host 1, host 2, and host 3. And also the task that we're going to do on each of the workers and the index. So this actually is the configuration, and it is definitely more complex than the one for a single machine. Now, when we are going to use it, it's very similar to the previous mirrored strategy. In this case, we use the distribute multi-worker mirrored strategy instead of mirrored strategy. And once we have created it, again, we use the scope to define where the where the tasks will basically be spread to, right? So after you define the scope, you do the class model definition, compile, and then fit. So as before, when you compile, we get the configuration of the different optimizer and layers that we have. And once you actually do a fit, that is when it will actually do the training, when it will take the batches of training data, mini batches from training data, and then actually split it into the different computational nodes. So in this case, the GPUs are no longer just on one machine, they're actually in different machines. So actually, when we do the spreading of this information, it has to go over the network. It's no longer just on the computer bus. So it's going to take a bit longer to do the fit, but you have more GPU resources available, so the computation uh, time will decrease, but the network communication time will increase because of the more complex layout of this particular multi-worker mirrored strategy. So this diagram actually shows the configuration in the case of the multi-worker mirrored strategy. We have multiple worker nodes. Each of these worker nodes has a CPU and a number of GPUs in it. So it is very similar to the mirrored strategy in the sense there's a mirrored variable, but instead of being just replicated into the GPUs on just one machine, we need to have a strategy where we actually distribute those variables into each of the GPUs on the other machines as well. Now, as mentioned previously, we actually have a class. When we have the cluster, we also have the host computer, which is actually the CPU address. So the CPU have to be still involved in coordinating with the other CPU because the training process is running on the CPU, and the GPU is only assisting in the mathematical computations. Now, even in this particular complicated case, it is still a mirror strategy. So the model has to be replicated in each of the GPUs. So each of the GPUs will have one copy of the model and will be training on part of the training data. So here there's a big speed up because we have many more computational resources available to do the weights update. But having more GPUs also means that when we want to synchronize the gradients that are computed in each of this. Remember, this is still a synchronous strategy. So at the end of each iteration, we do need to sync up all the mirrored replicas so that they will have the same values, right? Because we don't want these replicas to go out of sync, and then one copy is actually not the same as another copy in another GPU. So that syncing procedure now has a much bigger job because it needs to sync across many GPUs and work together with the other CPUs on the other worker nodes to coordinate this syncing process. So just a few lines of code as we saw in the previous slide, but a lot of things happen in the background. Another strategy that's very similar to the mirrored strategy is what we call the central storage strategy. So this is very similar to the mirrored strategy, not the multi-worker mirror strategy. So this strategy is worth mentioning because this applies to the special case where we only have one machine or one worker node and with multiple GPUs. So this is actually similar to the environment where we have the mirror strategy. But in this case, our GPU is not able to store the entire replica of the model because this replica cannot fit within the memory space of the GPU. So in this case, we designate the CPU as the central storage. So our CPU now does one extra work. Not only does it do the coordinating job, but it also acts as a storage area for all the model data in one central location. And it actually basically holds the global state of the model for each of the GPUs that's within the server. So this is different from the mirror strategy because in the mirror strategy, we actually have a replica of the model running on each of the GPUs. So we make use of the GPU memory, and therefore the communication is minimized between the GPUs. Here, the communication is sort of centralized at the server, at the GPU, at the CPU. So we try to reduce that communication, but obviously, since each copy has to now be sort of downloaded to individual GPUs to do the computations, there's going to be more communication bandwidth needed to actually send this data to the individual GPUs. But the advantage here is that we are able to store a larger model since we are able to make use of the larger RAM space that's available on the main server itself, rather than relying on just the GPU memory. Typically in a server, the CPU, the main memory for the CPU is larger than the memory that we have available in the GPU card. So just to give you an idea, the GPU maybe just it's just a couple of gigabytes, right? As compared with the tens of gigabytes that we are typically, or maybe hundreds of gigabytes of RAM available on the CPU server itself. So in this case, since the variables are not actually or the models not replicated in each individual GPU, the variables, they are not mirrored on the different devices, but they are all basically managed at the central point in the CPU itself. Therefore, in this case, the CPU sends the variable to the GPU side. That's what I said just now, right? There's more communication because we need to sort of download the variables to the GPU before they can start doing the training and compute the gradients and update the weights and then send back to the CPU where it combines it all together and then updates the model. Now, remember, the model is no longer in the GPU, it's actually centrally stored in the CPU's memory. So in terms of coding, it's very similar. We just need to initialize with the central storage strategy. And notice that in this case, we don't initialize how many GPUs we need since everything is stored in one central place anyway. And then we do the usual to actually distribute the data to the individual GPUs. So let me just say again that despite having different kinds of strategies, essentially this is still not model parallelism. These are still data parallel mechanisms. So the model parallelism requires you to use a different method. You cannot use any of the TensorFlow strategies for model parallelism. So model parallelism is not supported by TensorFlow distribution strategies. They are basically only supporting whether it is a mirrored strategy, multi-worker mirror strategy, or the central storage strategy. It is basically supporting only data parallelism. Is meant to make the computations shared across more machines or more GPUs, so that it can occur faster and we can get the results faster as well. So the training will take a shorter period of time. So we can see that all the memory is basically model is actually just stored on the CPU, and then we sort of download the model parameters or the variables to the individual GPUs for computation. So this is the central storage strategy. I know it looks very similar to the mirrored strategy, but just remember this: the model is no longer stored on the GPU as a replica. It is now only stored at the central place, the CPU. So previously in the mirrored strategy, multi-worker mirror strategy, as well as the central storage strategy, what we are doing is basically what's called synchronous training, because all the replicas have to be kept in sync. They have to basically mirror each other. Now, synchronous training has a lot of advantages because unfortunately, it can be a little bit hard to scale. One of the reasons for this is that some of the workers may be actually waiting for other workers to catch up because they have performed faster, and therefore they actually finish the task before the other workers. And because it's synchronous, they are not able to proceed because they need to actually sync up with the other copies that are running on the other worker nodes. So hence, this is one of the reasons why we have an alternative to synchronous training called asynchronous training. Now, if the workers are different in their capability, for example, some are faster and some are slower, or some of the workers are actually down for maintenance or have different priorities, then an asynchronous approach might be better because the workers do not need to wait on each other. A good rule of thumb is, of course, which is not applicable in all cases, is this: if we have small, unreliable, and limited capability devices, that means we have a heterogeneous environment and also more limited devices, it's better to use an asynchronous approach. On the other hand, if we have strong devices with powerful communication links, with high bandwidth communication links with each other, and each node has multiple GPUs, so they're all very, very powerful devices, then a synchronous approach is actually a better choice. It's just a rule of thumb. There are always exceptions to this, but generally this can be applied to help us decide on whether we want to have synchronous or asynchronous type of training. And one way to actually implement the asynchronous training is to use a parameter server. Previously, we talked about parameter server before, but it was in the context of a centralized versus a decentralized strategy. Okay? So a parameter server is a centralized strategy because we have one single point of coordination and it's not disputed in the network. But the parameter server can support asynchronous training. Let's see how this is possible. So parameter server training is common in the data parallel method to scale up model training on multiple machines. If you remember, the parameter basically gathers the gradients from multiple machines, combines them together, and then broadcasts to each of the individual machines at the end of the step. A parameter server training cluster consists of workers and parameter servers. Variables are created on the parameter servers and they are read and updated by each worker in each step. By default, the workers read and update these variables independently, hence the asynchronous nature. They do not need to wait for each other in order to perform the update. This is why parameter server style training is also called asynchronous training. Okay, so this is because they are not really dependent on each other when they do the update step. But the parameter server does need to wait for each of the workers before it can do the global broadcast. But individually, there's no communication between the workers to each other. So hence is called a asynchronous style of training with a centralized synchronization. Parameter server strategy. So parameter servers, these servers hold the parameters of our models, basically the weights of the model, and are responsible for updating them, the global state of the model. The training workers, they actually run the actual training loop. These are the ones that actually do the gradient descent and compute the gradients. And they also get the gradients from the loss function of the data. So these are actually the part that's running the fit function, right? They actually do the actual training itself with the mini batch data, and then get the output values and compute the gradients using the loss function during that fit function call. Now here's actually the complete flow. We replicate the model to all the workers because they all need to have a copy of the model. Each training worker then fetches the parameters or the weights, the current state of the weights from the parameter server. And then each worker basically performs the training loop, the fit function. Once the worker is done, it will send the gradients, right, for this particular iteration back to the parameter servers, which will then update the model weights. And then the cycle repeats again. So this is the parameter server strategy again being shown. So we have the parameter server which receives the gradients from the individual GPU nodes, and then it does a broadcast of the model to each of the nodes to update that global replica of all the models, because each of the GPUs is still actually basically supposed to have one common copy of the model, just that we have one central machine to sort of merge all the data from the various GPUs, the gradient computed by the individual GPUs. Now this allows us to train each of these workers independently, and they do not actually need to communicate with each other. They only communicate with the parameter server, and it also allows us to scale across many of these GPUs. Okay? So this allows us to run the training independently in each worker and scale across many of them. So let me just repeat again that this is a centralized scheme since we have one single parameter server or replicas for backup. And it is asynchronous because each of the worker nodes, they can work independently. So asynchronous training with a centralized synchronization mechanism. So you can use the TF parameter strategy, instantiate it. And for this to work, you need to configure the network configuration again. Specify what machines are available for the cluster, the worker nodes, the host and port address. And in this case, since we're using a parameter server, we also need to specify how many parameter servers there are. Typically, one of them is the main one, and then we may have more as a backup in case the main one fails. It is centralized, so it's a single point of failure. So it's good to have a backup parameter server. And lastly, we also have the task definitions of what we're going to do in each of these worker nodes. So we actually cannot support model parallelism, the one where we actually try to split the model amongst multiple worker nodes and not have replicas of the model. The model parallelism is more complex and we cannot support it with TensorFlow alone, but there is a software called TensorFlow Mesh that's actually built to support the model parallelism. So TensorFlow, with all the strategies, even the parameter strategy, essentially only supports data parallelism with its different built-in strategies. If we really want to implement model parallelism with a TensorFlow framework, then we would need to use the TensorFlow Mesh, which is given by this URL here. In the Mesh TensorFlow, we actually have a special language for defining how the updates actually work with the multiple layers being distributed across different nodes. So we need a special language to enable this distributed deep learning. So it's not the normal programming environment because this is a very specialized way of doing the gradient descent. And this is capable of specifying a broad class of distributed tensor computations. So because now we have coordination between layers rather than just replicating or synchronizing the entire model. So it's definitely more complex. And we can't do it with a normal mechanisms. We need this special mesh TensorFlow language to do this. And the purpose of the mesh TensorFlow is to formalize and implement the distribution strategies for your computation graph over all your processors. So as I said, it's a special language to define how you would actually implement the algorithm to synchronize the different layers together in the different nodes. So here's a quiz question for you. The TF mirrored strategy is designed for A. Several workers or physical servers with multiple GPUs in each server. B. Several servers with one GPU in each server. One server with multiple GPUs in the server. One worker with two mirrored GPUs in the server. So this is basically simple questions. So just pause a while and before going on to the further part of the video. Right, here's another quiz question for you. The TensorFlow Central Storage Strategy is designed for A. Several workers or physical servers with multiple GPUs in each server. B. Several workers physical servers with one GPU in each server. C. One worker physical server with multiple GPUs in the server. Or D. One worker physical server with two mirrored GPU in the server. So is it A, B, C, or D? So pause a while and then think of the answer before proceeding along in the video. So with this, we come to the end of the different TensorFlow strategies for implementing distributed learning using the TensorFlow mechanism, and also a quick intro to TensorFlow Mesh, which implements the model parallelism. So thank you for your attention.